Hello and welcome. My name is Acha,
I'm Rachel.
Eric.
and we are the Elks Golf Course Renovation team. So we're just gonna play a quick video showing you kind of a tour of the course. While this is going, I'll give you some background on the course. Kankakee Elks Golf Course. It's in Aroma Park, which is in Kankakee County, right next to the Kankakee River. It was designed by some pretty famous golf course designers, William B. Langford and Theodore Moreau in 1926. Yes, this is almost a 100-year-old golf course. As you can see, it has lush greens, and it used to be pretty popular. As the years have gone on, the attendance has kind of been dwindling a little bit, but it's still a great place to golf. Actually, our school's golf team goes out there to practice and things like that. Yeah, I think we get the picture. So, yeah, as I said, Kankakee Elks Country Club, one of the members of the club, Joe Giacchino, reached out to Reagan and mentioned that we might have some, there might be some aesthetic improvements we could make on the course to bring clientele back to the golf course. They kind of want to drum up their services a little bit. So our main objective has been to make a plan with these aesthetic renovations and also provide cost estimates for each section so they can take and leave what they need and what they don't need.
So when we were given this project, we divided it into 5 different areas with the need for improvement. So we asked the board what they thought that needed improvement, and also we talked to some of the members who were out there golfing when we went out for a site visit. And so these were the 5 main that we got from them. So that was the halfway house, gazebo, tree removal, stormwater design, and court path design. So for each one of these 5, we created a design objective. So for the halfway house, we want to improve the existing halfway house. It's in the back 9 of the course, and it's kind of falling apart and could use some improvement. For the gazebo, we want to provide a comfortable area to rest in the middle of the back 9. And then for the tree removal, we want to improve playing experience by removing obstructions from the fairways. For the stormwater, we want to reduce the standing water in the northern section of the golf course, which has some drainage issues currently. And then for the golf cart paths, we want to decrease the wear and tear on the golf carts and the golf course. So for each of these, we have functional requirements, which is how we're going to perform this design. So for the halfway house, we want to design a building that includes restrooms and an overhanging shelter. For the gazebo, we want to provide a shade and a rest area, as well as a shelter from the elements. For the tree removal, we want to eliminate any trees that add unnecessary pressure to the greens. For the stormwater, we want to divert the water buildup from the fairway to a designated area in the rough. And then for the golf cart paths, we want to provide a new path design with an improved material. And then we have a couple constraints for this. So as Acha mentioned, the course was designed by 2 very famous architects, so we want to maintain that historical significance, as well as maintain the difficulty of the course. We don't want to change any of the actual holes or anything. And then we also just need to adhere to all codes and standards for design. And then this is the design team. So first we have Acha, who worked on the gazebo and the trees. And then Eric is next, and he is the only one of us who has an architectural concentration. So he worked on the halfway house design. Then myself and I worked on a cart path design, as well as the engineering drawings for the stormwater design. And then Ethan worked on the stormwater calculations and design.
Like the team stated, the halfway house needs some work. As you can see, top left picture, the bathrooms are actually the right half of the shelter at the moment of the halfway house. The left side is a little concession area they had, but is no longer in working. So they wanted us to expand the restroom sizes, include some ADA accessibility restrooms, And we also had a chance for input from the golfers there, and they brought up a good point that they would like to incorporate a shelter. As you can see, there's only about a foot, 2 foot overhang on the roof, so it doesn't leave much space for a big group or a fair amount of people under there to get shelter from rain or like high winds. And then the right side picture is what our final design. Let's take a dive into it. As you can see on the right side, so that is the inside and the structural of the halfway house. Our columns are spaced 2 feet off the shelter, just so we can have enough room for our column footing. So for our accessibility, we had to follow all the ADA compliant standards. We went with ADA compliant sink and fixtures, ADA compliant toilets, ADA compliant rear wall grab bars and side wall grab bars. We also had to comply with their dimensions. The right side bathroom is 100% ADA compliant. The left side bathroom, however, sadly, we are short in our dimensions. However, we did incorporate everything ADA compliant still. Interior wise, these are some renderings. As you can see, we added 2 truffle lights to each bathroom. They're a great way for light and economical. The top picture is the bathroom that is not fully ADA compliant. Since it was not fully ADA compliant, we decided to add a urinal in there for cleanliness and accessibility for their golfers. The bottom 2 pictures are the fully ADA compliant side restrooms. As you can see, we are compliant to all ADA standards. Exterior wise, we went with shingles roofing. For the structure was in really good shape, so we didn't change anything. But on the exterior, for aesthetics, we decided to do metal sheeting siding. As you can see, also our columns are wrapped 3 foot high with brick. We did that to protect the columns, the longevity of it, and also for aesthetics. On these elevation drawings, you can see we also added some exterior lights. I know people don't golf at night, but however, maybe they have groundskeepers come out really early or really late after a big day of golfing. So just for safety reason and aesthetics, we added a couple barn lights on the exterior. Now, once we finished our design, we had to move on to seeing if our design was going to stay up with all the loads and everything. So to start off our design calculations, we had to start off by finding our dead and light loads, which we used the ASCE standard for minimum design loads for buildings and other structures for these equations. The top equation you can see is our roof snow load, which is a dead load. We got 12.6 PSF. We use that value then to find our slope roof snow load. Since our common residential trusses are 4/12 pitch, we ended up with 12.6 PSF still. Then once we found our dead load, we had to find our live loads. And our roof live load is 20 PSF. That 20 constant is just for our region, how much pounds per square foot of snow we get. So as you can see, 20 is greater than 12.6, so that will be our load that controls. Following that, we had to do our beam and column design. For that, we used the NDS National Design Specification for wood construction. To start off our beam and column designs, we had to follow the load path. So from the roof, we already found our dead and live loads, so then we follow to our beams. Our beams are going to be the ones that are going to hold our trusses that are gonna be used for the shelter. So after we ran through that calculation, we got 875 psi. Then we had to find the bending shear for that same beam, which is 135 psi. After we found that and it passed all our standards for our beam, we had to follow the load path again to our columns. Following that, we had to do column stability factors. We used that value to find our column compression design, and that is one of the most important equations, because if our column fails, our structure fails. And one of the first things following, once again, load path, our column would be one of the first things to go. Thankfully it passed. As you can I was just so our trusses, top left picture, we use common residential trusses, 16 feet long and 412 pitch. Top right picture, we are using 2 by 12 by 8 beams. We're gonna use two staggered on each other as the beams, by the way. Our columns are 6 by 6. Now moving on to our footing. Our footing is based off on our load path again. There's per the International Building Code, there's a specific amount of load that becomes our minimum. So we fell under that load. So we just had to, we didn't even have to calculate, we just automatically reset to the minimum, the 18 by 18 by 12 per the International Building Code.
So moving on to the gazebo, there is currently one gazebo on the golf course at the southern end. Initially, we were looking at it as more of an auxiliary project just because it was already constructed and it just seemed like it was some minor problems with rot maybe, so it would just take some patching. But the more we looked at it, the more we saw it's actually significantly rotted, and also there's a pretty bad side sway issue, so next time there's a big wind, it's coming down. So in the end, we decided to go for more of a redesign than a renovation. Also, when we talked to the board, they mentioned that there used to be another gazebo at the north end of the course, and we actually found an aerial photo of it there, right next to the pond. They said it used to be pretty popular with like wedding parties, taking pictures and stuff like that. So they mentioned that they might want to replace that, but in the future, use a material that's a little more water resistant. That's actually why this one is not there anymore. The water from the pond would get all over the structure and it caused even more rot than was in the last one. So they ended up taking it down a couple years ago. So those were the two gazebos that we really wanted to focus on. Instead of just doing something from scratch, we decided that it might be a little more efficient to just go to a gazebo company that would make a gazebo kit so that you could put it together yourself or just pay someone a less steep fee for construction. So we actually found a local company, Country Lane Gazebos, and they provided us some renderings based on the images that we presented and also some measurements that we gave them. So the one to your left is the one that would be next to the pond. You'll see it's a different color. That's because it has a vinyl wrap around it, which would be a little more water resistant. It's also a little smaller, a 12-foot diameter, but the style is very similar to the one on the right, which would replace the one that you saw in the picture. Very similar style as well. It's a little bit bigger, 14 feet. And unlike the other one, this one won't need a foundation from the gazebo company, because the one that's already there seems to be in perfect order. It's really just the wood that's deteriorated over time. But the pond gazebo will definitely need a foundation because that was removed with the original structure. Moving on to tree removals. So actually when the original design of the course was laid, there were no trees in this area. You can even see in the picture on the left that was taken in the 1980s. This is hole 8 on the course, and there are hardly any trees near the fairway, just a few you can see speckled throughout. But this current picture here to the right, you can see there's a plethora of trees, and a lot of them encroach onto the fairways and choke up that place near the hole. So trees are a necessary hazard, or at least some view it as a necessary hazard. But if it overcomplicates the play beyond what it's designed to be, then it can be a little superfluous. So we decided that we would take some trees out just based on some of our findings. These are those said findings. We made a little equation. We took the width of each fairway. We took some widths where there was some blockage from the trees. We would take the full width of the fairway, and we'd also take the width that a branch would stretch out onto the fairway. We would take that ratio and then find the average of all those lengths we took. That was about 30 or 40. So the average of those were 11%. So that means 11% of the fairway length is covered by trees, or fairway width is covered by trees. But there were 3 major outliers that were much higher than 11%. And those are at holes 6, 8, and 16, which are indicated here in the picture. It was ranging between 40 to 60% obstruction, which is a lot more than I think is necessary. So those were our main target points when we were considering removals. Here you can also see those same areas, and you can see the specific trees we're thinking about removing. The ones indicated, that's 8 right there, but it could range between like 7 or 10 that they end up taking out. It's really up to the discretion of the country club. So, like I said, 5 to 10, 7 to 10 trees to be removed. When we're thinking about removing these trees, we have to think if we need to get a permit. In the Kankakee County ordinances, they include tree removal in this term called stripping, which is really like any removal of land. So in that ordinance, they have a rule that if it's in excess of 5,000 square feet, then you have to get a permit, except for a few minor exceptions. So our entire area of all 3 holes does exceed 5,000, but if we break it up to each hole is less than 5,000 square feet. So that means that if we broke it into 3 different cycles or 3 different fiscal years, then we could not have to go through the gymnastics of getting a permit for that. And that might make it a little easier on the board of the country club moving forward. However, they did raise some skepticism over if they could get their independent contractors mobilized for all 3 of those cycles in time. So we will present both options to them, and again, it is at their discretion.
So the next step of our design project is the stormwater design. The goal for this is twofold. So the first goal is to decrease the flow of water flowing through the course. And then the second step is to allow the water other places to flow that are not on the fairways. So the detention basin completes this first goal by decreasing the flow of water. This is a term known as attenuation. And then the French drain satisfies the second goal by allowing the water to flow beneath the fairways. So in the detention basin, there's 5 steps to complete this design. The first is to delineate the watershed. The second is to compute the peak runoff, then design the actual basin, then to compute the outflow hydrograph, and finally to provide the engineering drawings. With the French drain, what it satisfies is carrying water beneath the fairways. It also provides essentially an underground detention area for the water to be housed. So the first thing we need to understand is why and where these problems are occurring on the course. So to kind of get an idea of where we're at on the course, you can see the Kankakee River to the west, the clubhouse to the north, and Highland Road to the east. In the middle of the photo, you can also see there is a darker colored area of grass. This is an old creek bed. It's lower than all the surrounding areas, so it gets wetter faster than the other parts of the course. It runs perpendicular to the fairways, so it crosses 3 main fairways, the most notably being the first fairway. This makes your impression of the course, so it's important that you have a good impression when you start playing around golf here. So these are the issues with the ponding, and this is the area that we will focus on. So the first step to our stormwater plan is to delineate the watershed. We were able to do this by uploading a topographic map into ArcGIS and running a watershed tool. The watershed here is outlined in pink and has an area of 0.06 square miles. Our GIS was then used to find our hydraulic path. So you can see here the lighter blue is the smaller tributaries, while the darker blue shows the larger tributaries and higher flow. We can see from these hydraulic paths that the water flows from east to west here, meaning the water is draining towards west towards the Kankakee River. The next step then is to compute the peak runoff. So the first equation here we use to find our excess rainfall and runoff. The first thing we need to know is our curve number. Our curve number is found from the hydrologic soil groups located on the course. This is found on a USGS map. And then the second thing is to determine our rainfall intensity. So this was a decision we had to make whether we were going to design for a 10-year storm, 50-year storm, or a 100-year storm. So in this photo, you can see that the area shaded in blue is the floodplain zone for a 100-year storm. So the majority of the northern portion of the course obviously is covered in this floodplain zone, so obviously a 100-year storm wouldn't be feasible to design the detention basin for. The next equation then is our peak runoff equation. So this is found multiplying the runoff by the drainage area, which we have found earlier, by the unit peak discharge. So the unit peak discharge is found from our time of concentration, which is the amount of time it takes for water to flow from the furthest point of the watershed to the point of interest. By multiplying these numbers together, we can find that our peak runoff is 10.5 cubic feet per second. So with that, we can also find a synthetic runoff hydrograph. This is calculated based off of empirically determined factors. Essentially, a runoff hydrograph is the amount of runoff flowing into the basin over a given period of time, still with that 10.5 cubic feet per second peak runoff flow. The next thing we need to do is we need to design our detention basin. So the two key things to do here, first I'll say, so first you can see that this is the cart path right in front of hole 18, or fairway 18. You can see the detention basin is towards us on the right, and the cart path is going across right there. It's raised, and it acts as a berm to hold the water into the detention basin. So with the detention basin, we have a volume of around 30,000 cubic feet. And then the cart path that is raised acts as an outlet structure. So there is a pipe running down beneath the cart path. It is an 8-inch pipe. It acts as an 8-inch orifice. And then the cart path itself on the top acts as an emergency overflow. For the detention basin, you can see the cross-sectional view here. You can see that it has a height of 2 feet. That the water will be held behind. That's on the right side is a detention basin. On the left side is where the water will flow out of it. The pipe diameter is 8 inches, as mentioned previously. The total width of the berm itself is 11 feet, while the actual gravel cart path is about 5 feet. So then the next step here is to calculate the outflow hydrograph. We did this using the NRCS reservoir routing method. Again, it's important to note that our goal is to attenuate the water and slow down the flow from the inflow to the outflow. This is reducing our peak flow. So based off the volume and the outlet structure of the basin, we are able to compute the discharge at each elevation within the basin. This allows us to compute the outflow over a given period of time. And so we can see a decrease of peak flow from 10.5 to 8.5 cubic feet per second. So that means that the basin is doing its job and attenuating the flow of water.
Okay, so I created this plan in AutoCAD of the whole stormwater design that you can design. So it shows the basin, which is up on the top right, as you can see, which is 15,000 square feet and then 30,000 cubic feet. So next on the drawing, we have the raised cart path, which you can also talk about. So that will drain out into that brook. Then under the first fairway here, we have a French drain, which the details will be shown on the next slide. But that runs under the first fairway, and then it will empty into an underground gravel detention area, which will be 3 feet wide and 4 feet deep. This is basically just a place where the water can collect underground instead of on top of the fairways, and then it can be allowed to percolate instead of having standing water on the course. So then the water will go under the 9th fairway, which is another French drain, designed similar to the one under the first fairway. And then the natural slope of the land will take it into the bed of trees off to the side. So this is the French drain design that we created. First, I'm just going to explain what a French drain is, and then explain this design. So it uses a perforated pipe, which means that it has holes all around its circumference, so that water can enter in from all sides. It sounds kind of counterintuitive, but the French drains work by allowing water to flow in from all sides, especially from beneath. So a French drain is a ditch in sloped ground inset with perforated pipe under a layer of gravel. And its function is to funnel the stormwater away from where you don't want it, basically away from the fairways and into the rough. So for this design, we have a 2-foot deep trench and with 2 6-inch pipes, perforated corrugated PVC pipes underneath. We have 2 pipes because it will, we have 2 pipes instead of 1 to allow for maximum water flow. The gravel that we're going to use must be at least 1/4 inch in diameter. The pipes and the gravel are encased in a non-woven geotextile filter fabric, which will help prevent soil and debris from clogging the French drain. The gravel is filled up to a few inches below grade, so that way on top you can put some soil and then grass, so that way it hides the whole French drain and you can't tell that it's there. So for the slopes of these, the French drains should have a slope of 1 inch for every 8 feet in length. That's typically recommended. For the most part, we're relying on the natural grade of the land, but some of the fairways are not super sloped. So Ethan went out a few weeks ago and took some elevations with surveying equipment, and the first fairway has a slope of 5 inches, only 5 inches across, which is not a lot. So that one will definitely have to be sloped more when it's designed or when it's implemented. But the 9th fairway has a slope of 17 inches, so that will only need an extra couple inches of slope when the pipe is put in. Okay. So moving on to the golf cart paths. So last semester was heavily research based for me. I did a lot of research on different materials and design, and then this semester I did a lot of work in AutoCAD. So when I did this research for the paths, I found several factors that will influence the design, which being traffic intensity, funding available, the stormwater runoff, ease of maintenance, and then strength and durability. So these are a couple of the materials that I've been looking into. Some of these are commonly used on golf courses across the United States. So these are gravel, asphalt, concrete, and a permeable paver material. So I created this table of each of these, and with the research that I did, and a few things I want to point out on here is, you'll notice the lifetime of gravel is a lot more than any of the other ones. It's double all of the rest of them. And then for the prices, these are per 100 feet of path, so it's not the total price, it's just based on a 100-foot basis. And then permeability, we're looking for a permeable material because we don't want to increase the stormwater drainage issues we have with ponding, so we want something that will allow water to flow through it. So after I did all of that research, I created this decision matrix, which bases, so I used like these words. Okay, these factors, yeah, that's okay, there we go. Based off of each of these factors, such as price, strength, lifetime, etc., and I rank them good, or if they're poor, if it's a good score. If it's good, it's a high score. So you can tell from this that the True Grid, it's a permeable paver, has the highest score, but you can also see that this other permeable paver got a score of 24, and gravel is close behind with 23. So any of these are a good option for the path. We recommended the True Grid permeable paver, but when we brought this to the board last semester, they decided that they wanted to go with gravel for the path design because it's the cheapest, and that was their highest priority, was the price because of funding. So they chose gravel, so that's what we went with for this semester for the design. So this is the design that we created. So it's a 6-inch deep gravel path based off of the Gravel Roads Maintenance and Design Manual. That's the typical recommended depth. And then to prevent weeds from growing and to keep the gravel all in the path, we want a woven geotextile fabric that will just keep it all together. And then most cart paths are about 5 feet wide, so we just kept that the same for the design. And then also we want the path to have a crown on it a little bit, so that way it's not completely flat. So that way this will prevent water settling on the path, and then if the carts drive on it, it will create depressions in the path, which we don't want. So the recommended slope is a 1/4 inch per foot, which is a 2% grade, as shown here.
So to wrap up our Elks Golf Course redesign, let's take a step back to our halfway house. So the way we broke down the pricing for this, we went interior and exterior, kind of like how an actual contractor will split up the pricing for the halfway house. Some factors are going to be plumbing, electrical, and framing that has to be done inside, which they will charge for labor and material. For exterior, there are going to be some structural work, some heavy machinery. They will charge for labor and material as well. We came out to a final estimate of $35,000, which is $73 per square foot.
For the gazebos and the tree removal, since those were a little more simple design-wise, we were able to reach out to the contractors directly and get their initial quotes. So for the 2 gazebos that were mentioned earlier, each one would be around $5,000, so that total would be around $10,000. As for materials, I'll check and see if it's for labor and machinery. For the tree removals, we actually reached out to a company that has worked with the country club before, A&R Tree and demolishing, or demolition, I guess. And they gave us a quote of about $1,500 to $2,500 per tree, depending on the size and the height. So that would be around $15,000 for the whole project. That does depend on if they're splitting it up into 3 different cycles, like I mentioned before. But the total cost of those 2 sections should be about $25,000.
Finally, we have the stormwater and cart path cost estimates. So some of the factors that influence the stormwater cost estimate are listed below. The first one is the physical things that need to be done. So that includes the trenching, the piping, the backfill. And that then is broken down into material, labor, equipment, and then overhead and profit. Another factor that would influence the cost would be an engineer's approval. So it would cost for a professional engineer to design and sign off on this design. We also need to factor in the cost to maintain the pristine environment. So a construction company would charge an extra amount of money to maintain the sod and the grass without tearing too much up. Also, a factor that we take into account is fluctuating material labor costs. So with all of that, we are able to provide a final estimate of $80,000 for the stormwater portion of the course. And then the cart paths, because they chose gravel, we can estimate about $5,000 per 100 linear feet of cart path installation. Here's some of our references. Any questions? 35 minutes.